The study of mathematics is like the study of a new language. You must learn to recognize and know the meaning of symbols and the meaning and definition of words used in mathematics. You must build your vocabulary with practice and application. So we begin with the introductory chapter 0 about a basic component of mathematics called numbers, something everyone knows about and is in use every day. The real number system. Numbers are everywhere. We use numbers in many different ways. In everyday usage, numbers are used to measure, to count, to compare, to identify, catalog, gamble, make phone calls, count money, and so on. Everyone can identify with the application of numbers in one way or another. In general, everyone knows how to use numbers in their own way and needs. In order to advance forward in the study of mathematics, it is necessary to establish a nomenclature of the various types of numbers we have, based on their specific application. What we are doing here is also called the classification of the number system. We must add to our vocabulary the distinction each type that the numbers share. So we start with the simplest set of numbers common to all, which is the counting numbers, called appropriately the natural numbers. So, the natural numbers. These are the natural numbers. 1, 2, 3, 4, 5, and so on. There are no fractions, decimals, or negative numbers in this special set, and no zero. We use these for serial numbers, barcodes, catalog numbers, phone numbers, and so on. In mathematics, we have two applications actually. Quantity, called nominal numbers, like how many marbles are there in that bag? The other, the order, called ordinal numbers. Who came first? Who came second? Who came third in a race? For example, the mathematics symbol for this set is capital N. Next come the whole numbers. Next to the set of natural numbers, we add a 0 and call it the set of whole numbers. 0, 1, 2, 3, and so on. The mathematics symbol for this is capital W, or sometimes N subscript 0, sometimes even the capital letter Z. What is the big deal about adding 0 to the natural numbers that make it so much different? Well, if I asked you how many marbles are in the bag, 0 is a possible answer. But if I asked you who came in 0 position in a race, well, it does not apply. So natural numbers and whole numbers distinguishes the sets which includes 0 and 1 and not the other. Historically, the idea of using a 0 cipher in numbers was not introduced in mathematics until much later in the writings of earlier counting numbers. Distinguishing between types of number sets is extremely important in the study of mathematics. The study of exponents is an example where this is applied, and you will see that in the next chapter. Next up in the hierarchy of numbers are the integers. We are adding now to the number set we started. The integers include the whole numbers and negative counting numbers. 0 does not have a negative sign. The integers are, going to the left, -1, -2, -3, and so on, and to the right, 1, 2, 3, and so on, with 0 included in the middle. Or we can write it in a different way. 0, comma, plus or minus 1, comma, plus or minus 2, plus or minus 3, and so on. The symbol for this set is capital I. Our number system is growing. The next group both positive and negative, are the decimals and fractions which are lumped together because, surprisingly, they are of the same type. We call these the rational numbers. A finite decimal like 3.5 can be written as a fraction 7/2 or 3.5. An infinite decimal like 3.3333 is called repeating infinitely and can also be written as a fraction 10/3 or 3 1/3. Quite simple. All decimals, fixed and repeating, can be converted to these simple fractions. This set is named the rational numbers. The symbol for this set is capital R and includes all the integers that we talked about earlier, obviously. All the sets of numbers above are considered to be exact. The type of number not included so far are called the irrational numbers, and these are inexact when converted to decimals. These cannot be made into fractions. When these types of numbers are used in calculations, the symbol of the number represents its exact value, but as a decimal, it cannot be always shown as an exact value. The symbol pi is one example. If calculated to more decimals, the list is infinite and non-repeating. Other symbols in use to represent numbers are the square root of, the cube root of, the fourth root of, and so on. Trigonometric functions are other examples. The symbol for this set is capital R bar on top. When you combine the rational set R and the irrational set R bar in one entire set, this is referred to as the real numbers. That is the end of the story about the nomenclature or classification of the real number system. Can we go on, or is this the end of the story on numbers? Yes, we can go on and add even more numbers to make a bigger set. We have complex numbers to add in what we refer to as encompassing all of the above. The complex number system is what it is called. You will see this number further on in your studies in the chapter on quadratic equations. Now, it begs the question, can we add more and more? No, that is all there is when asked, how big is our number system? We are now going to discuss the properties of an algebra. What follows is technical jargon, only important to career mathematicians, and the average student in a mathematics course will not have to bother with this. But for the sake of completeness, I have included what is referred to by mathematicians as the properties of an algebra. There will be no questions or tests relating to the properties of an algebra. The general properties of an algebra. There are operations that can be done with an algebra, and they are specifically as follows. A and B are elements in a set. The set may be the real number system or parts of it, like the natural numbers would be a part of the number system. In the first one listed as a property is closure. If we take the natural number system, for example, the counting numbers 1, 2, 3, and so on. If you add two numbers, one is A and one is B, like 2 and 3, and you add them up, the result is still a member of the natural number set. It's not a fraction or anything like that. It's the same for multiplication. We call that closure, belonging to a closed club. 2 plus 3 is 5, or 2 times 3 is 6, and 2 and 3 and 5 and 6 are all members of the club or of the set capital N. The commutative property is second. If you take two natural numbers and add them or multiply them and turn them around and multiply and add again, you get the same number. That is to say, 2 plus 3 equals 3 plus 2 equals 5. Same as 2 times 3 and 3 times 2, and that equals 6. The next one is associative. You can add any two numbers together and add a third number to it in any order that you like. So A plus B plus C is the same as A plus B plus C, and the same applies to multiplication. This doesn't sound like very much, but it is important in our vocabulary and future studies in mathematics. Next is the 0 and 1. 0 and 1 are like neutralizers, so to speak, in mathematics for addition and multiplication respectively. For example, if you take the number A as equal to 3 and you take an integer minus 3 and add 3 and minus 3 together, you get 0. So then you know that one is the inverse of the other. And in multiplication, the inverse for A might be like 3 multiplied by a third is equal to 1. So 3 and a third are inverses of each other. Division by 0 is an exception and is meaningless. The distributive property, A times B plus C is equal to A times B plus A times C, or in other words, we can put it the other way around. B plus C multiplied by A is equal to B times A plus B times C, because both results have the same effect. There are no other basic properties to study for now, and there is only multiplication and addition forms of operations basic in mathematics. The explanation of the general properties of an algebra is summarized in this last page.